Hello and welcome to the topic of hardware testing with Python and FLooPy. My name is Friedrich Hagedorn and today I would like to show you the possibilities of FLooPy on a demonstration example. The concept and the features of FLooPy I already introduced in the last video. The link is in the description below. Let's go! Let's assume we are a battery manufacturer and we want to offer our customers an individual test report as a PDF file for the battery they have purchased. In this example, we will limit ourselves to the following three test parameters. Firstly, this is the open circuit voltage, and secondly, the internal resistance when charging and discharging the battery. The goal now is to determine by measurement whether these three parameters are within the expected limits. My measurement setup for this looks like this. I've connected a power supply to the battery, which is the device under test. This allows me to set the charging current and measure the battery voltage. For discharging, I use an electronic resistor decay to raise the load current, and both devices are connected to a test server via USB. In the software, I always naming the instruments from the perspective of the device under test. So in this case, device under test.battery stands for the power supply, which measures the battery voltage, and device under test.load stands for the resistor decay. Okay, now let's take a closer look at the second test case. It's about determining the internal resistance when charging the battery. We write all the things we need for this test in a Python class. Each test case can have both input and output parameters. With an output parameter, we also specify our expectation, which means that the pass-fail value is determined using the lower test limit and the upper test limit. The test case now starts with a setup function in which the current and voltage limits of the power supply are set. Then we have the actual measurement task, where we set the charging current, wait a short moment, and then measuring the battery voltage. However, to determine the internal resistance, this measurement must be repeated several times. Now there are basically two different configuration options for this loop. Either a loop with fixed values can be configured, or we can leave it completely free and only configure the loop in the next hierarchy level using the current input. This gives us a greater flexibility. When we have finished the actual measurement, in the teardown function, the battery is switched off again from the power supply. So, finally, we come to the evaluation, where we use one or two regression lines to first determine the polynomial coefficients and then the internal resistance of the battery. And now we can see very clearly that there is a separate function for each test section, which are linked to each another using variables. Okay, once we have created the other test cases in this style, we put them all in a separate library and use this to create the test plan now. To do this, we load our test library and first select the test for the open circuit voltage. In the second test case for the charging process, we now have the option of configuring the open input parameters, which means we can now specify here whether a parameter is just a constant number or it's iterated in a loop. For example, the charging current is iterated in 40 equal steps. The min-max limits of the interval can either be specified as here or omitted. In this case, the previously defined default values of this input parameter are used. In the third test case for the discharge process, we have to raise the load resistance. To do this, we use a logarithmic scale. And finally, we create the desired PDF report. Basically, our test plan is now fully configured. If necessary, this configuration could also be used in the next hierarchy level, but we will stick with it and want to execute the test plan. But for this, there is one last important point left. We still have to define the test environment for the device under test. To do this, we load another library for the instruments and put together our measurement setup. For our simple example with just two instruments, there are actually only two relevant lines. However, you can also use other test environments in the same way. Let's take a look how this works. I've connected the battery to the two instruments and connected them to the test server via USB. In my case, this test server is a small CMA board here below. And we will now continue working directly on the test server using a browser IDE. I have opened the file with the test plan on the right hand side, and in addition to the last slide, I have not only defined a test environment for the real instruments, but also added an environment for a simulation model and a manual measurement. We will look at all three cases and start with the simulation environment. We also need a so-called data manager whose task is to save the loop states and the measurement results. If we now run the test plan, the simulation is done quite quickly. Two files are now created, the PDF file from the test plan, and by default all internal variables are saved in a JSON file. Now let's take a look at the PDF file. This is now the example datasheet, and all the results obtained from the measurement are shown in color. You can see here below in the fairly accurate diagram the voltage curve during the discharging and here above during the charging process. Here in the table above we can see the pass-fail values. The limits within the test are passed are shown in brackets. Well, so much for the theory. Now we move on to the real measurement, which means we simply have to change the test environment and run the whole thing again. Of course, the real measurement takes a lot more time. Now we are in the second test case, where the charging current is increased step by step, which is shown here on the power supply in yellow in the second line. And we can clearly see how the battery voltage also increases here in green. Now we are already in the third test, where the load resistance is decreased by the resistor decade, and you can see in the first line in green how the voltage continues to fall step by step. The PDF file is now being created and we can update it. Now you can also see in the diagram that this is a real measurement. However, if you take a closer look at the measurement data from the charging process in the upper curve, you can see that there's a slight bend in the curve, so that this straight line is not a good fit of the measurement data. And that's why we are now trying to fit the measurement data with two straight line segments. For this purpose, I have prepared a variable in the second test case that stands for the number of line segments. We are now changing this from 1 to 2, and I designed my software in such a way that you don't have to repeat the entire measurement just because something changes in the evaluation. Instead, you only need to evaluate the relevant variables again. At the moment, a few low-level calls are still necessary for this, but these can be done even more nicely. In the diagram, you can now see the two line segments, which now fit the measurement data much better. I have not further analyzed the electrochemistry of the battery here, I just want to use this example to show the possibilities of subsequent post-processing. Finally, I would like to show how we can use exactly the same test cases for a manual measurement. The only thing we have to do now is to select a suitable test environment. If we now run the test plan a third time, we will be guided through the measurement. First of all, we are asked to switch off the power supply output. This is already off and I can simply acknowledge. Then we are asked to measure the battery voltage. We read 1.34 volts. The next three settings do not require any changes. We can simply acknowledge. Only the voltage limit needs to be increased from 1.7 to 5 volts. Then we acknowledge. Now we can switch on the power supply output and acknowledge. Now we should measure the battery voltage. It's 1.49 volts. Then the charging current should be increased to 10 mA and acknowledge. Read the voltage 1.56 volts. Now the charging current should be increased to around 20 mA, acknowledge, and read the voltage again 1.61 volts. And so on. So you can see that you are guided through the measurement and therefore careless errors can be avoided, assuming you stick to the instructions. Well, to summarize, you can take two things away from the demonstration example. Firstly, you don't have to commit to a specific test environment when writing the test functions, but you can abstract the measurement setup and so get a readable testing guide. And secondly, the test plan is just a configuration file and the entire data flow is done automatically by FLooPy in the background. In this way, FLooPy can be used to test a wide range of electrical products. This can be, for example, individual sensors or a complete embedded system. If you are curious now, then try out the minimal example on the GitHub page and feel free to contact me. Have fun and good luck with hardware testing. Bye bye!